All right, good morning. I'm Luciano Smith from Southwest Research Institute, and I'm going to be talking about some probabilistic analysis of cold earth holes, in particular fatigue crack growth analysis that we have been doing primarily for the U.S. Air Force, and with the complicating factor of the engineered residual stresses from cold expansion of the holes. And then after we talk about some of that work, we'll get a little more specifics into the probabilistic aspects of it at the end. So fatigue crack growth analysis, for those of you who are more in the stress life or strain life world, we're using linear elastic fracture mechanics to calculate K, stress intensity factor at the crack, and which is a factor of those few things that I've listed here, and I highlighted residual stresses because that's the one complicating factor in these analyses. We're calculating K, we're calculating the cyclic loading that gives us a delta K. From that we get our DADN, and we can determine what the crack growth is for every cycle that's experienced by the crack. So cold expansion is a process that's used very commonly in the aerospace world, where you are essentially just pushing a mandrel through a hole, the mandrel being slightly larger than the hole, usually on the order of 3 to 4%. And what this does, it imparts some pretty significant compressive residual stresses around the hole, which can be really valuable in terms of fatigue life. Often we can get 5, 10, 20 times increase in life from doing this. This top right is a video. Can you start that video for me? So this video here just shows the process of cold expansion, which hopefully we can get to. Yeah. So this just shows the process. You're drilling a starting hole, then you're going to ream it out to the starting diameter. After that, you'll see a little quality control step of verifying that starting diameter and checking the size of the mandrel. So here's quality control, checking the size of that hole diameter, making sure that you're within the required range. And then here's the mandrel that's going to be pushed through the hole. And that's approximately the same size as the hole, but you'll see in just a second a little sleeve getting slipped on. So that sleeve stays in the hole. And so now when the mandrel gets pulled back through, it's too big for the hole. So that's where you're imparting a lot of residual stresses there. You see that strong compression right next to the hole edge. And then you pull that out and again, do some quality control, and then finally do a final ream. So we'll skip the rest of that. So the benefit of that, like I said, it gives you much longer fatigue life on your critical holes in the structure. The problem for us as engineers is it makes the determination of the life of that crack quite a bit more complicated. And so the Air Force for a long time has used a fairly simplistic method to account for this. They essentially just make the initial flaw size smaller, and that gives you a longer life. But that can be fairly inaccurate depending on the differences in the geometry and material that you're working with. And so we and some of our Air Force customers about 10 years ago, and some colleagues at other organizations, started a group called ERSI, which is the Engineered Residual Stress Implementation Working Group. It's a collection of folks who are working with the Air Force to understand the various aspects of characterizing and analyzing residual stresses in metallic parts. So you can see the group that was at the last workshop a few months ago. There's the website if you're interested. It's just residualstress.org. And we're working towards not just analysis, but also inspection, quality control, residual stress measurement, lots of different aspects of this problem. Oh, I've lost control. Yep. Thank you. So one of the things that we do as part of ERSI is some analytical round robins, which have been really valuable for understanding just the different methods that people use for analyzing these types of problems. And so here's one that we did a couple years ago where the Air Force Research Lab ran a bunch of tests. I believe these were 7050 aluminum, just dog bones like this with a hole, an initial flaw. And you can see there were 4 different conditions that were tested. Non-cold expanded holes with constant amplitude loading. That's kind of our baseline simple analysis to verify that everybody's running the problem correctly. And then we add the one complication of variable amplitude loading. Then we go back to constant amplitude loading, but with the cold expanded hole with the residual stresses. And then finally, we add get to the most complicated and realistic problem of the cold expanded hole with variable amplitude loading. There were a handful of different folks who entered analyses into this round robin, and each of the entrants were given a few different aspects of the problem. So you can see the material data, strengths, toughness, fatigue crack growth rates. We also were given measured residual stress fields. So for 17 different holes, they were measured, the residual stresses were measured with either the contour method or with X-ray diffraction. And we ended up with full field residual stress fields that were measured using these different methods. So you can see here just kind of a mid-plane residual stress field. You can see that strong compression down here by the hole edge, and then it gets up here to some residual tension farther away from the hole. We were also given the flight spectrum that was experienced by the variable amplitude specimens. And these were realistic flight loading, followed by some marker bands for post-test fractography. So my co-author and I each ran an analysis using one of the 2 programs that we typically use for fatigue crack growth analysis. So AFGRO is a program that was originally developed by the Air Force and is now sold commercially. And so my co-author ran his analyses using AFGRO. And then NASGRO is a program that was originally developed by NASA and is now jointly managed by us at Southwest Research and NASA, developed and also sold commercially. And so I ran the analyses using NASGRO and one of the weight function models there. So I was able to impart the residual stress field into the model that way. So Dave, my co-author, and I made different assumptions for the residual stress field. So you can see his here in the red with some of the data that he used to make that assumption. So he used a lower bound of the nominal measured residual stresses. And then my analysis used more average values for most of the field, but right at the edge of the hole, I reduced those residual stresses by quite a bit. You don't see that in the measured data, but there's quite a bit of uncertainty and question about the accuracy of those measurement methods right at the hole. And thought it was best to reduce that. So different assumptions, but in the end, it didn't make a whole lot of difference, fortunately. So here you see the results from the round robin for each of our 4 different configurations. So this is the open non-cold worked hole with constant amplitude loading, non-cold worked hole with variable amplitude loading, cold worked hole with constant amplitude loading, and cold worked hole with variable amplitude loading. And my analysis with NASGRO is entrant 1 in the red, and Dave's analysis with AFGRO is entrant 2 in the pink. So you can see in the first one here, that was a very simple problem. We've got the red and the pink. They're both pretty accurate and pretty conservative. There's really very little variability in all the different analyses. This is kind of a verification of a fairly simple problem. Then we add the complication of variable amplitude loading. You see a little more variability in the different analyses. We add more complication with the residual stresses, more variability, and then finally the residual stresses and the variable amplitude loading, and you see the most variability, which makes sense. Fortunately, both Dave and I had what I think are fairly good results in the pink and the red here. You can see mine here goes a little unconservative, and that's primarily just because of the assumption that I made as far as load interaction, crack growth retardation Um, so that is the round robin analysis that we were part of. And then we wanted to work through this as if it was a more realistic problem for a real critical location on one of the aircraft that we help to manage. And so we used a program called Nessus, which is another program that we developed. It's a probabilistic analysis software that allows you to tie into any of your standard deterministic analyses and use various probabilistic methods, sampling methods, and most probable point type methods. And so what we did is we linked AFGRO to Nessus using a Python script, and we incorporated a handful of random variables. So here you see what those random variables are, and we picked the random variables and the distributions based on what we think would be realistic in terms of what we might, the kind of uncertainty we would have in a real analysis. And from there, we looked at the variability in the life results based on those distributions. And you can see there's pretty widespread here. So if this were a real location and we were using this as kind of a digital twin to understand what kind of a life we'd have on a particular aircraft for this critical location, we'd have a pretty widespread and we wouldn't be able to manage that very well. And so we use Nessus to output importance factors and probabilistic sensitivities to help us determine what we should reduce the uncertainty in. And so you probably can't read that since I can't even read it from up here, but this is stress scaling. So this is kind of the uncertainty in our loading. This is D80N, so the variability in our crack growth rates, and then CX, so this is our residual stress field. And those are the three primary parameters that give us the most uncertainty. And so that would allow us to see basically what we would need to track or get more data in to reduce the uncertainty, to be able to provide a better, less variability in our results and a better result to know how to manage this aircraft. And so we can reduce the uncertainty in loading by adding aircraft data recorder with individual aircraft tracking to understand the loading sequence a little better. We can also perform spectrum testing to reduce the uncertainty in our load interaction effects and determine a good retardation parameter to use. And that allows us in the end to just kind of run these different analyses again with different uncertainties, different hopefully reduced standard deviations in our distributions that will reduce that variability. So hopefully we get to something more like this, where our spread here in terms of the analysis results is quite a bit reduced. So that's the end of what I have. And I'm happy to take questions.